Well, good morning, everybody, or good evening. So today we start the topic compactness. This is chapter 2, lecture number 3. And we start from recalling what are compacts in Rn. So in finite dimensional setting, so in Rn, in a Euclidean space, a set is compact if and only if it is bounded and closed. And such sets, so compacts in this space, they are important, for example, for continuous functions, because in connection with, so continuous functions defined on compacts, they have particularly nice properties. In particular, a continuous function on a compact set is bounded, uniformly continuous, and the image of a compact set under a continuous mapping is again a compact set. Moreover, a continuous function on a compact set, I mean real valued continuous function or complex valued, but okay. Now, scalar function on a compact set attains its minimum and maximum. And also a continuous function on a compact set can be uniformly approximated by polynomials. This is the famous Stone-Weierstrass theorem. So the questions which we are interested in are, can we do something similar in infinite dimensional setting? So what are then the compacts? Is this true or not? So what are the compacts? Which good properties they have? So how far can we extend this picture to the infinite dimensional setting? Okay, so we start from definitions. So let X tau be a topological space and A a subset of this set X. A family U lambda with parameter lambda, which belongs to a parameter set big lambda. This set can be very, very fat, probably very, very uncountable, but anyway. So any arbitrary family or collection is called an open cover of the set A if all sets in this family, they are open sets, so that is, they are elements of our topology. And they cover the set A, that is, the A is a subset of this union. Okay. And now definition 2, the main definition of this chapter, so that's why we will write it down. So let X tau be a Hausdorff space. So we will consider only this case. Of course, we can define compacts also in the general settings, but the more general setting we consider, the less nice, the worse the properties have the compacts. So let us focus on the case of Hausdorff spaces. In this case, the properties are still quite nice. So we consider Hausdorff space a set K, which is a subset of X, is called compact or a compact. So it depends on you if you like to have it adjective or noun. It's called compact if each open cover of K contains a finite subcover. Probably I can write it down in a more detailed way. So each cover, and we call it U lambda, lambda in lambda, contains a finite subcover, that is U lambda 1, U lambda n. So only finitely many sets, and this is related to the name, to the word finite, and subcover means that K is covered by this union, I from 1 till n, U lambda I. I guess this definition is well known for you because actually in analysis one, so in finite dimensional setting, this definition is also mentioned that a compact in Rn is exactly the object which is described by this definition. And then you see that the definition is totally abstract and does not give any impression what is it a compact set. And then there is the statement like this that a set is compact only if it is bounded and closed. So now why do we need this abstract setting? So actually this definition is very helpful in the technical sense. So when you prove something, so this is exactly the proper definition to use to prove something. Okay. One small remark. So a set K is compact in some topological space, Hausdorff space X, if and only if this topological space, what does it mean? So we consider K on its own, and we consider the induced topology. So the topology on K induced by the topology tau in X. So this is the definition of this topology. So a set K is compact here if and only if it is compact here. So as a compact space, so to say. But I guess this is obvious via the definition which we have here. Okay. So here we have a proposition with, so to say, a basic properties of compacts, and we are going to discuss it and also prove it. The proof is very easy, and the idea is to show how helpful the definition, this technical abstract definition of compacts can be. So proposition 2.4. So if we have a compact in a Hausdorff space, so then, first statement, a closed subset of a compact set is again a compact set. Each compact in a Hausdorff space is a closed set. Then, an image of a compact set under continuous mapping from a Hausdorff space to a Hausdorff space is compact. And the fourth statement that each infinite subset of a compact set has a limit point in K. I do believe that these statements are probably known or quite easy. So let us look through the proof. So first, let us prove this first item. So the proof will be given on slides because we don't need to write it down because they are simple, and the idea is to look how this definition works. So we prove the statement number one: a closed subset of a compact set is again compact. So we assume that we have a subset of K which is closed, and we take any open cover of this set. Then we can add this set to this open cover. Since A is closed, this guy is open, so this is an open cover, and this open cover covers everything. So the whole space X in particular, also the set K. So this is a new open cover of our compact K. Then by definition, there exists a finite subcover of K. And hence, this is a finite subcover, covers not only K, but also its subset A. That is, what does mean finite subcover? It contains finitely many sets of this form, and probably also this set. Probably. But anyway, if it is like this, then we can just throw it away. And this would be the finite subcover of A, yes, because this set, of course, does not cover anything. I mean, any point of A is not covered by this set. That's it. We have proved number one. So are there any questions concerning it? Okay, seemingly everything is fine. So let us fast run through all other steps. So everything, again, very simple using this abstract technical definition. So let us prove statement number two, that each compact in a Hausdorff space is a closed set. So assume that K is compact, A is a set Sorry, I guess I just, okay, copied the slides. Okay, forget it. We prove two. Each compact in a Hausdorff space is a closed set. So, okay, our assumptions, the space is Hausdorff, K is a subset of X and is compact, and we take any point Y which lives in the complement of K. So we want to show that this point belongs to this set together with some neighborhood, with open neighborhood. That is, we want to show that this set is open. So this is what we have. Then, since our space is Hausdorff, for any point of X, there exist two neighborhoods, so two open sets in our topology. So one set is Ux, this is a neighborhood of X. Another set is V with index Y, which depends on X. This is a neighborhood of Y such that these two neighborhoods, so these two open sets are disjoint. They do not intersect. This follows from the statement that X is Hausdorff. Okay, so when we consider such such family of open sets, Ux, this is an open cover of X, yeah, because each point of X is covered by the corresponding open set Ux. Okay, since K is compact, there exists a finite subcover of Xk. That is, there are finitely many points, x1, xn, so that the corresponding neighborhoods make this finite subcover. So let us consider then, for each open set here, there is the corresponding set by the construction, the corresponding set Vy of this point. So consider all this Vy of xi. We have finitely many of them, so we consider this intersection. So this guy is an open set for each I. So intersection of finitely many open sets is still an open set. So I can write down that this belongs to tau. And of course, all these guys, they are neighborhoods of Y. So Y belongs to this intersection. This is one hand. On the other hand, all this intersection is a subset of this space, or of this set. Why? Because we have a finite subcover of K. This means that K is a subset of this union. But by our construction, so this intersection is disjunct with this union. And hence this intersection does not contain K. And hence we have this inclusion. So what is the conclusion? We have shown that for any arbitrary point in this set, there is an open neighborhood which still lives in this set. That is the space, the set, sorry, is open. And hence K is closed. Okay, are there any questions? Okay, thanks for the feedback. So we go further. So let us prove item number 3. So an image of a compact set under continuous mapping is compact. So let us consider two Hausdorff spaces. X is a subset of X and it is compact. And we also have a mapping from X to Y, which is continuous. And we take arbitrary open cover of the set F of K, so the image of K under the mapping F. This is a set in the space Y. Okay, so we fix this open cover. Then we consider this family of sets. Since F is a continuous mapping, pre-image of any open set is an open set. This is what we have discussed last week. So these sets are open, and then by the properties of pre-images, this family is an open cover of the set K in X. Then, since K is compact, there exists a finite subcover, which looks like this. So finitely many sets of this type, finite subcover of K, and then again using the properties of pre-images and images, this family is finite subcover of this set. And that's it. So we have proved that any open cover of this set has a finite subcover. Any questions? Is everything clear? Thank you. So here should be 4, of course. So we prove item number 4. Each infinite subset of a compact set has a limit point in K. So we consider an infinite subset. We consider a countable infinite subset, so we can count the elements, so it is a sequence. But this sequence contains not, how to say, so as a set, it is an infinite set as a subset of K. That is, there are infinitely many different points in this sequence. Okay, so we consider such a sequence, and we assume that there is no limit point of the sequence in this set. So what is the conclusion? This means that since there is no limit point of this sequence in K, this means that for each point x of K, there exists a neighborhood of x, which is exactly what is written here. So it's an open set which contains x, such that this neighborhood contains at most finitely many points of this infinite set. Yeah, so there is no limit point. That is, any point in X is not a limit point. And then this means that there is a neighborhood of each point which contains at most finitely many points of Xn. Perfect. So we have, for each X, we have constructed an open set with some properties, but this means in particular that this family is an open cover of K. Then we can take a finite subcover since K is compact. And what does it mean? So K is a subset of this finite union, but each element in this union contains at most finitely many points of this infinite set. And this union is also finite. So this union contains only at most finitely many points of Xn. And so this statement means that this sequence, so this sequence is a finite set, but this is I don't remember how to say it in English, so I always said it in German, so it's a Widerspruch, and in Russian it is противоречие, but in English I don't remember how to say it. Maybe you can help me?
Contradiction.
Contradiction, yes, thanks. So there is a contradiction with our assumption that this is an infinite subset. Okay, an infinite subset, so set of infinitely many elements. Okay, so you see again this step that we can take a finite subcover from a cover, open cover. This makes the deal. Are there any questions or comments?
I'm sorry, is it true that in Hausdorff space maybe we can use proposition and in proof say even that Ux contains 0 points of Xn?
No. Well, probably I don't understand the question, but in Hausdorff space we said that. So first of all, what was the definition of a limit point? It was the definition was that any open neighborhood of this point, which is a limit point of a set, any neighborhood contains at least one point which is not this x, particular x, but belongs to the set. And we have proved that in Hausdorff spaces it is the same. It is equivalent to the statement that each neighborhood of this limit point contains infinitely many points of this set.
So by definition, I suppose we now can say that if x is not a limit point, then there is ux such that not contains points of k.
You mean except x?
Yes, that's except x.
Yes, yes, yes. I mean, I suppose.
Yes, yes, I understand. Yes. Probably yes, but I'm not sure that this really improves.
Yes. It will not. We still can prove, but I suppose in that case we will get a contradiction that xn is not a finite set, but it will be an empty set even.
Yeah. You're right. Yeah. Yes, you're right.
Thank you. It's still. It's not important, but interesting. Sorry.
Yes, why not? Yeah. So once again, not once again, was just a small remark that when you listen to some lectures, there are some proofs, and sometimes one might think that, okay, so there is the unique way which is correct, but this is not the case. So actually there are many ways, and there are, so to say, standard proofs, which are probably the shorter or the shortest proofs, or they are, so to say, standard in the way that you just using the same tools you can prove many different things. That's why I presented. But actually, it does not mean that you should always think standard and proceed in a standard way. Yeah, so there are a lot of ways for creativity how to prove something. You're always welcome to think your own way, but just use a proper logic. Okay, but nevertheless, we have proved proposition 2-4. Once again, as a summary, if we have a compact in a Hausdorff space, then a closed subset of a compact set is compact. Each compact is a closed set. Image of compact set under continuous mapping is compact, and each infinite subset has a limit point in the compact. Remark, so again, so this statement number 4, be careful. Proposition 2-4 does not imply that any sequence in K has in K a convergent subsequence. So this is again the story that if the space is sufficiently fat, so the convergence so to ensure the convergence, we should run over uncountably many neighborhoods, and this, so to say, this picture does not correspond to the convergence of a sequence. So there is an exercise which exactly corresponds to this remark. So we consider this space. This is a product space. So we have so many copies of the interval -1, 1. We have discussed it last time that this space is just a space of functions from R to this interval -1, 1. So this is a product space, which is a nice topological space with product topology, which is also called Tikhonov topology. And I will just, in the next slide, I will formulate the theorem, Tikhonov theorem, which says that if we have a product, arbitrary product of compacts, then it is a compact in Tikhonov topology. So the statement is that since this interval -1, 1 is compact, then a product of such compacts, so arbitrary product, is again a compact space. So this is a nice compact space. And so the task would be to show that this sequence of elements, of course, these are nice functions defined on the whole R and take these functions take values in this interval. So show that this sequence does not have a convergent subsequence. I recall that convergence in Tikhonov topology means pointwise topology, pointwise convergence. That is, this sequence or any subsequence of this sequence converges in this topology. This means that it converges at any point t of this, or any point t of R. So this is an exercise for you to show that there is no any pointwisely convergent subsequence of this sequence. And so you see, this is a finite subset of X. It should have limit points by this statement, but there is no a convergent subsequence. Are there any questions to this exercise remark?
So we need an additional axiom of separation in order to have this.
We need
in order to work this for this remark to work, right?
No. So once again, so this is the statement which is correct for any compact in any Hausdorff space.
Yes.
So if we want this to be how to say, so once again, there is a limit point in K for any infinite subset, but this does not mean necessarily that there is a subsequence which is convergent. So
Yes.
if you
So
want to make
what do we need to add to this
to make something like this, yeah?
Mm-hmm.
So there should first countable space. The space should be first countable. In particular, in the
Mm-hmm.
metric space, everything is fine, and we will
Yeah.
discuss it in later on. So what does not work here? It is presented by this exercise. So we have a very fat space, fat in the sense that in order to so we have this topology, and the convergence in this topology means pointwise convergence. And in order to control this pointwise convergence, we really need, so like we have a sequence of elements in this space. And in order to have this sequence converging somewhere, so like xn converges to x in this space, in order to check it, we need to use uncountably many neighborhoods of this guy in this space.
Mm-hmm.
So not countably many, but uncountably many. So for example, in a metric space, we can create, as I said last week, we can create such family of neighborhoods of this point x, and this is a countable base of neighborhoods of this point.
Yeah, this is exactly the property that we have in this first axiom of separation.
Yes.
Yeah.
Yeah. So if we can, so to say, reach the point by using countably many basic neighborhoods, then that's it. But in this case, this is not true. The space is too fat. We need uncountably many neighborhoods because each neighborhood contains only finitely many coordinates, and we have so many coordinates. So uncountably many coordinates. Okay. Further questions?
What is theorem 2.6?
Yes, it will appear in the next slide as soon as we are allowed to go there.
Okay.
Yes, so this is theorem, which I have already announced. Tikhonov theorem, which says that the product of any collection of compact topological spaces is compact with respect to the product topology. Well, this is the reference where you can find the proof. So this is not the main material of the book, but like a more advanced material. So we have no time and energy, at least I have no time and energy to prove this theorem in the frame of this lecture course. But this is a very important result in general topology. So please remember it. And in particular, yeah, the spaces of this type are very nice spaces due to this theorem. So they are compacts in Tikhonov topology or product topology. Okay, so yes, I will be sufficiently fast today in the sense that there are a lot of slides and not that much to write down, but I hope that roughly speaking, what we discuss is a generalization of known things, so we can run sufficiently fast. But please, if I am too fast, please stop me. Okay, so next proposition. So now we have two metric spaces, and K is a compact in X, and we consider a continuous mapping, then F is uniformly continuous. That is, for any epsilon positive, there exists delta positive, such that for each 2 points in our compact, such that the distance between them is smaller or equal to delta, we have that distance between their images is also small, controlled by this epsilon. I guess this is just obvious statement. Aha. Again, it is a slide which should be deleted, and this is the final version how it should look like. So there are two statements. So first statement is that if we have a continuous mapping of a compact to a metric space, then this mapping is uniformly continuous. We have just discussed it. And in the second statement, so if this space is just real numbers with standard topology, or scalars, so complex numbers fit as well, then F attains its global maximum and minimum. Everything can be proved in a very standard way, just using the proofs of analysis 1 and using distances instead of absolute value. So this is an exercise for you to check that everything is still working also in this more general setting. Okay. So it was like a forward. So what we have done, we just introduced the notion of compacts in a Hausdorff topological space. And as I said, the definition is very abstract, but very helpful technically. But then the second question is, okay, we have a compact set. By definition, it is compact, but okay, we have a set is given. How to check if it is compact? Because physically, in the reality, it is not possible to check that any open cover has a finite subcover. So by hands, how to do it? It is not that trivial. So of course, there are a lot of criteria that in the space of this type, the compact sets have this structure of this form. Like in Rn, we said that a set is compact if and only if it is open, if it is closed and bounded. So the next step would be to consider some criteria, how to check that a given set in a given space with sufficiently good properties, if this set is compact or not. And the first
Excuse me.
step in this direction, yeah?
Can you go back to the previous slide? So you mentioned that Y can be a set of complex numbers, right?
No, yes, it was a wrong statement. Yeah, global maximum, minimum.
But yeah, so it will be the global maximum of the absolute value.
Yes.
Mhm.
Yes.
Yeah, thanks.
Also in the N. Yeah, so it's not totally ordered. Yeah, so so let us stay here. And of course, you can extend this to finite dimensional setting in a proper way, so to say, if it is possible. Yeah.
Yeah, we need to get something one-dimensional like
Yes.
norm.
Yes. Okay, thank you. Yes. So now we go to, so to say, special case of Hausdorff topological spaces, namely metric spaces. And the aim is to obtain a criteria to understand the structure of compact sets in metric spaces. And then after that, we will consider particularly interesting metric spaces and discuss a particular criteria in these particular spaces. So something which is useful for application. So how to check if a given set is compact in the reality. So we need first a couple of definitions. Probably you know them, probably no, but let us go through. So we have a metric space and a set in this space. So first definition, we take any epsilon positive, and a set E in X is called an epsilon net for A if for every point small a of this set big A, there exists an element E in this set big E, such that the distance between A and E is smaller than epsilon. That is, this means that we can cover our set A by open balls with radius epsilon, centrums in the points of this epsilon net, and so the cover over all balls. Yeah, the points from E are called nodes of the epsilon net. Yeah, so I hope this is clear from this statement that for any point there exists element of E such that this holds. That is, this point lives in the corresponding ball. Okay, so this is the definition of the epsilon net. Then a set A is called totally bounded if for every epsilon positive there exists a finite, so this is the important word, finite, epsilon net for A. That is, for every epsilon positive, A can be covered by finitely many open balls of radius epsilon. And once again, totally bounded means that for every epsilon, this construction is doable. Any questions to these two definitions?
I mentioned this analogy with phone connection, and so it has this areas of coverage from one antenna, and like the first property says you that like all of your citizens are covered with network, and like each antenna has some radius epsilon, and like for each person gets the connection, and like the second property says like doesn't matter how like small the radius of coverage is, you can always like attain it with finitely many antennas. I don't know.
Yeah, thanks. Interesting. Yeah. Okay. Remark. If A possesses a finite epsilon net, then there exists also a 2 epsilon net of A whose nodes are elements of A. So in this definition, E is just a set of X. So these elements E, they don't need to be in A. But since we have this, we can just expand each ball to make it twice larger and shift the radius so that the centrum is not in this E, but in some other E which belongs to A. I guess it's clear how to prove it all. I will draw something until you are thinking and I am drawing. So this is a ball of radius epsilon. So this is my E, and it covers some points A. So now you can consider this A as the centrum of the ball. Yeah, and then you need radius, which is like this. So if you take 2 epsilon, you are sure that you will cover okay, it is a centrum. Okay, you are sure that you will with this centrum Yeah, so this ball covers this smaller ball, and then if we had epsilon net for A based on these red balls, then this 2 epsilon net of blue balls will also cover the whole A. Okay, sorry for my bad pictures, but I guess it is clear. Yes. So in the sequel, we will always assume that we consider epsilon nets, which are built from the elements of the set which we are interested in. That is, we construct an epsilon net for A, then we take elements of A for making nodes of this net. Okay, let us go further. It was the first part of the remark. So second part of the remark, if X is totally bounded, then X is separable. So this is a proof. So indeed, if we assume that X is totally bounded, then for each n there exists a finite 1 over n net of elements of X. Okay, then the union of all the nodes of all the above 1 over n nets is at most countable and is dense in X. That's it. Yeah, so once again, we take 1 over n net of elements, so of elements of X. Not just net for X, but a net which consists of elements of this set itself. Okay, we go further. Thanks for the feedback. One more statement. If we have an epsilon net for A, then this net is also a 2 epsilon net for the closure of A. This is again an exercise. So we do not discuss it, but hopefully it is quite clear that we can add all the limit points if we make our balls a little bit larger. Okay. So conclusion from this statement number 3. So if A is totally bounded, then the closure of A is also totally bounded. Yeah, because for each epsilon there is a finite net for this set. Well, I guess it's already the time for example. Yes? Not yet. Okay. Question?
Excuse me, when we formulate this remark 2 and 9, it's in general setting or in... sorry, it's...
we are now living in metric spaces, yes.
Yes, sorry.
Yeah.
Net doesn't have sense not in metric space, sorry. Okay, thank you.
Yes, because as soon as we need both, we can live only in metric spaces, yeah. So as I said, the definition of compact set is that from any open cover you can find a finite subcover, and this definition works in totally general setting, even beyond Hausdorff topological spaces. But the more general space you consider, the less good properties you have. In particular, if the space is not Hausdorff, then there are compact sets which are not closed. So everything becomes worse and worse, so to say. So in Hausdorff spaces, we can use, roughly speaking, only this definition about open cover and finite subcover. As soon as the space becomes better and better, we have more, how to say, okay, we have some more description. What is a compact set? So in the first step, what is the compact set in the setting of metric spaces? And now we discuss the notion of total boundness, because this is a, so to say, an ingredient which replaces the notion of boundness, which is needed for compacts in finite dimensional spaces like Rn. Okay, so once again, a set is totally bounded if it can be, so if it has epsilon net for any if it has a finite epsilon net for any epsilon. That is, the set can be covered by finitely many balls of arbitrary small radius. In particular, yeah, 1-point set is totally bounded, yeah. Okay, so remark continues. So statement number 4, if a set is totally bounded, then it is bounded. But if it is bounded, it does not follow that it is totally bounded. So let us first think about this. What does mean that A is totally bounded? This means that A is a subset of finite of such union. So finitely many balls of finite radius. Well, it's a bounded set, yeah? Because you can always find R big enough so that all this finite union of balls live in such a set. It's an exercise for you. Everything is simple here. Now the opposite is not true. So if a set is bounded, then it does not mean that A is totally bounded. And I guess there will be some examples how to which show this. So we go further with examples. So in the setting of finite dimensional spaces, so X is equal to Rn, then boundness and total boundness, it is the same. That's why in analysis 1, nobody discusses this total boundness. A justification. So if A is bounded, then A is a subset of this rectangle. Yeah. So if we choose n sufficiently large, so instead of a ball, so A is bounded if there is R such that A is a subset of such a ball, but instead of a ball, we can also use this rectangle. Better to say a cube, n-dimensional cube. Okay, but then this is a picture about the epsilon net, not epsilon, but the net of this size for this nice cube. I guess you are welcome just to look at the picture and you agree that this is a nice totally bounded set, and hence A itself is totally bounded. Agree? Okay.
So we divide our district
Yeah.
in order to cover it with network.
Yes. Okay. Now, second example. Now we have a space small L2. So this is the space of all sequences such that so this is small L2. This is a space of sequences, so infinite sequences, such that the norm is finite. So this is the metric in this space L2, and now we consider a set which looks as follows. So A is a unit ball in L2. That is, it is a space, the set of all sequences such that their norm is small or equal to 1. So this is like a distance between this element X and the element 0. Yeah, so this is a unit ball, and we consider a closed unit ball because here we have smaller or equal to 1. Okay, then this state, so this space is bounded. Yes, open ball, yeah? A is an open ball, so by definition, it is contained in a ball of finite radius, so it's a bounded set. But this set is not totally bounded because this space now is infinite dimensional. So indeed, let us consider the basic vectors of this space. So E1, this is a vector with coordinates 1, 0, 0, 0, 0, then second vector 0, 1, 0, 0, 0, etc. So there are infinitely many these basis vectors in this space, and they all, of course, belong to this unit ball. They have norm 1. And it holds then the distance between two basis vectors is exactly square root of 2. Hopefully it is, yeah, as in finite dimensional case, everything is the same, but the problem is that we have infinitely many basis vectors which have norm 1, so they belong to this unit ball, and the distance between them is square root of 2 for different indexes. Hence, there exists no finite epsilon net for A if epsilon is smaller than this number. Yes, because, yeah. So this is like E1, this is like E2. So if epsilon is small enough, then in order to cover both elements, we need an independent ball. So one ball for E1, one ball for E2, etc. So in order to cover only this sequence, we need infinitely many balls if the radius is small enough. So there is no finite epsilon net for the whole unit ball, since even this subset is not, we are not able to cover this subset with finitely many balls. Okay, this is a kind of a standard example which is used in many different situations. So please remember this construction.
And by the way, the same construction is often used to show that the closed ball is not a compact in L2. So we can already see some connection.
Yes, that's true. But not only in the L2. So the similar
Yeah, sure. In infinite
considerations can be proceeded in many different, not in many, but at least in some of different settings. Yes, we go further. Next example. We are again in L2, small L2, but now the set A is the so-called Hilbert cube. Actually, Hilbert, better to say Hilbert brick, so kirpich. So it looks as follows. These are all elements of the space L2 with the following requirements. So in each next dimension, the size or the length of this brick is twice smaller than in the previous dimension. So it's really like we have in the first dimension, then in the second dimension, then in the third dimension, smaller. So like a brick. And then the problem is that we have infinitely many dimensions. In particular, one can check that there is no open ball inside this Hilbert cube. So this set does not contain any open subset in this standard metric and hence the corresponding topology. But the statement is that this space, this set is totally bounded. So it is an exercise for you, but I will give, of course, a few comments. So we take any epsilon, fix it, and we want to construct an epsilon net for this A. So how we do it? So we consider n big enough such that this guy is smaller than epsilon, starting from some n. Probably so. I'm not going to solve the exercise, but give a hint. So starting from some n0, the difference in all the tail coordinates, so yeah, all the tail coordinates, the difference will be smaller than epsilon. So roughly speaking, we can neglect these coordinates. And then the first coordinates, there will be finitely many. And for this case, so we consider, so to say, we consider vectors of this form. Yeah. And then we use this nice epsilon net, so to say, to deal with finitely many first coordinates. And then since all the rest coordinates, they vary very, not far, they lie, so to say, not far away from zeros, they're smaller than epsilon, everything will be covered. by a ball with the radius epsilon. Yeah. I'm not sure if I was completely understandable. Have you understood what was the idea?
No, I did. And I think this example is also like it gives good intuition about compacts in infinite dimensional spaces. So as I heard, we can say that they cannot be like thick. So
Yes.
they can be thick only in some finite number of dimensions.
Yes.
But when we go higher, they need to become shallower and shallower.
Yeah.
So they are like almost like a
they do not contain an open ball, yeah, because we go in this situation again.
Yeah, so they need to like shrink with more dimensions.
Yes.
That's the only way.
Yes. So once again, so this guy is totally bounded, and this guy does not contain any open ball. As soon as there is an open ball, we are here, and this space, this set is not totally bounded. Okay, let us go further. Example part 4. Let X and Y be two metric spaces, and let the set A be totally bounded, and let the mapping be uniformly continuous. Then the image of A under this mapping is also totally bounded. This is an exercise for you. Everything is standard there, so there is nothing to discuss. But when I say this is an exercise, this means that please try to do it, because it's really a practice how to proceed with rigorous proofs. So standard technical things, but they should be, a mathematician should be able to produce them as well. Okay, now interesting things, or not interesting, but more advanced things. We have some time. Okay. So lemma 211, let XD be a metric space. A set A in X is totally bounded if and only if every sequence of elements from A possesses a subsequence that is a Cauchy sequence. This, I suppose, to write down the proof slowly so that you can follow. So if and only if. So we have two directions. And let us first prove in this direction. So now the true lecture, I write on the blackboard, so to say, and you follow my notes. Okay. So let A be totally bounded. And let us consider a sequence of elements which belongs to A. So since A is totally bounded, there is a one net a finite one net for A. Of some balls of radius 1, and of course we always assume that we take a net using the elements of A itself. So again, so it's so finite one net, so a finite cover of A. That is there exists at least one ball. We will denote it as U1 of this one net, such that this ball contains infinitely many elements of this sequence. Yeah. So A is covered by finitely many balls of radius 1. At least one ball should have infinitely many elements because we have this subset of A. It is covered by finitely many balls. So yeah. So like next step, we consider, oops. So consider only what is happening here inside this unit ball. So in the intersection of A and this unit ball. Since A is totally bounded, then of course its subset A intersected with U1 is also totally bounded. Totally bounded. And hence there exists a finite 1/2 net for this set. And hence there exists at least one ball which I will denote U2 of this 1/2 net such that this U2 or U1 intersected with U2 contains infinitely many elements. Of the sequence. And then we do this inductively. So induction. That is for any natural number n, there exists an open ball un of radius 1/n such that this Vn, which is the intersection U1 intersect with U2 intersect, etc., intersect with Un, contains infinitely many elements. Of this sequence. So this is already almost everything is done. So in each Vn, choose an element x with index kn. This is an element of this sequence. Such that kn plus 1. So this index kn plus 1 is bigger than the index kn for any n. Since each Vn contains infinitely many elements, so we can do it. So we first choose an element in V1, then in V2 we choose all the elements. We choose element with this condition because there are infinitely many elements. We can do it, and so step by step, inductively, we can create what we want. So after this construction, we have a subsequence. It is a subsequence of our sequence. And this subsequence is a Cauchy sequence. That's because Vn lives in an open ball of radius 1 over n. That is starting from any fixed n here, all the tail of the sequence lives in the ball of radius 1 over n. That is, the elements of the subsequence, they become closer and closer to each other. So, is it clear with the proof?
Yes. I like that here so we don't need to say that xn has different elements, or like we need to choose xn that is not the same as the previous xn, because so in this setting our sequence can be just sequence of one same element, and the proof works
Stationary sequence, which consists of only one element. Yes.
Yeah, we just need to take the next index, and we don't care about the equality or inequality between xn's.
Yes, I didn't stress it in order in order not to be misleading, but that's great that you notice it yourself. Yes, that's true.
I think the version that I remember, there are a few additional steps were needed to say something about different x's. And one point is that, so this may look a bit technical and some words, but I really like the fact that this is basically the same idea with when we prove that the segment 0, 1 is compact, right? So we divide it in half each time, and on every step we assume that somewhere there we have infinite number of elements, and we continue this procedure and get a contradiction. So basically we have the similar procedure, but we cannot divide in half because the structure is unknown, but we can use this construction with shrinking balls.
Balls, yeah. So as soon as we are in metric spaces, it is not a big deal in comparison with a segment or interval, or in R1. So just intervals, instead of intervals, you have balls. It's enough. Yeah. In more general setting, it's not that easy when you don't have balls, but still, in some cases, one can survive with neighborhoods. Okay, so this was the proof in one direction. So if a set is totally bounded, then we have this nice statement that each sequence has a not convergence, yeah, but a Cauchy sequence, a subsequence, a Cauchy subsequence. For the convergence, we need completeness of the space, but so far we don't need it. So opposite direction, we prove in opposite direction. So we assume that every sequence of elements possesses a Cauchy subsequence. So let me somehow, I wanted to make it blue. Let me call it, this would be property sharp. So we prove now that if we assume this sharp is true, then another assumption that A is not totally bounded. So BDD means bounded. So what does mean that A is not totally bounded? So I write down the negation that there exists some epsilon positive such that there exists no finite epsilon net for A. So we assume that this property is fulfilled, and we assume that A is still not totally bounded. Then we show that there is no epsilon net, so we will prove it. We will prove that there is a problem. So this is what we assume. So what we want to prove. Then we construct, sorry. We construct a sequence AN, sequence of elements in A, such that distance between different elements of this subsequence is strictly bigger than epsilon for any different indexes. So we construct it as follows. So take any element A1 in A. Then there exists A2 in A such that distance between A1 and A2 is strictly bigger than epsilon. Why such A2 exists? Since otherwise this set which consists of only one point, this set is epsilon net for A. But we assume that there is no finite epsilon net for A, for this epsilon. Hence, this A2 exists. Agree? Everything is clear so far?
Yes, yes.
Okay, then take any A3 in A such that distance between A3 and AI is bigger than epsilon for I equal to 1 and 2. Again, this A3 exists, since otherwise this set A1 and A2 would be is an epsilon net, a finite epsilon net for A. So you see, this is the construction. So you inductive, we construct the sequence AN such that this sequence has the property which we have already announced. Okay. So using this assumption, that is, there is no finite epsilon net for A. Using this assumption, we have constructed a subsequence of elements, a sequence of elements. So I should emphasize that this is a subsequence of elements in A. Yeah. But there exists no Cauchy subsequence for this nice sequence AN. Yes, because all elements are far away from each other. They are not getting to be closer. They are always separated by epsilon. So all elements of AN. That is, no Cauchy subsequence is possible. And this is a contradiction with our assumption.
By the way, I don't know how to say it in English. It's called расставленная последовательность.
I also don't know.
Yeah, maybe there's some term like.
Probably no idea. No, I don't know.
Mhm.
But again, this is a kind of standard constructor which one should take into account that this can be used in many different situations as a counterexample. Okay, so we have proved the lemma.
I'm sorry.
Yes.
What is it enough for us to finish the proof? Just if we just stop on the second A. So if we have A1, A2, and they have distance between them is epsilon, and if we take subsequence A1, A2, A1, A2, A1, A2, it also will not have no, okay. Sorry.
Yes, it will have.
Sorry.
Yes, it will have.
Yes. Sorry.
Yes. But thanks for the question. It's very important to think, to think how we can play, what we can do, what we cannot do. So you're always welcome to try to change something, optimize, consider from different points of view. It's a very, I like the way of thinking, so to say. Yes. Okay, so it was the lemma. The lemma is needed, so we are finished. So may I go further?
Yes.
Okay.
Yes, this is a Boltzmann Weierstrass lemma, right?
In a sense, yes.
Mhm.
In a sense, yeah. So yes, so we have succeeded to do it in a very brief. So now theorem 212. So this is a kind of a criterion how the compact sets and metric spaces look like. So theorem 212, we have a metric space and K is a subset of X, so the following conditions are equivalent. So first statement is that K is compact, and then criteria. So second statement that every infinite subset of K has a limit point in K. Third statement, every sequence of elements from K possesses a subsequence converging in K. So this is again what we have discussed, yes, that the limit point is not the same as a convergent or a Cauchy subsequence, yeah? So in the metric spaces it is equivalent. And the fourth statement, K is totally bounded and complete. In particular, if the metric space X is complete itself, then K is compact if and only if K is totally bounded and closed. And this is a kind of, so compare. So if we were in Rn, so K is compact if it is just bounded and closed. But as we have clarified, in infinite dimensional setting, totally bounded is not the same as bounded. It is a finer, a stronger property. And then in metric spaces, the picture is, so in complete metric spaces, the picture is as follows. It's totally bounded and closed. Okay, so this is a characterization of compacts. And so this is an important result. And let us prove this theorem. So first of all, let us show that statement number 1 is equivalent, it implies statement number 2. So it follows from proposition 2, 4. So we have already discussed it in the setting of Hausdorff spaces. Of course, metric spaces are Hausdorff. So if we have a compact, then every infinite subset of K has a limit point. I hope that you still remember that we have done it today. So now, next step, we show that 2 implies statement number 3. So X in K be a limit point, of an infinite set. So we have infinitely many different elements in this set, and this is a subset of K. Yeah, so not a stationary sequence, yes, but a sequence which contains infinitely many different elements. For each open ball with radius 1 over n and centrum in center in this point X, in this limit point, choose an element X Kn, an element of this sequence, such that Xkn belongs to this ball, and Xkn is not the same as this X. Since we have infinitely many elements in this sequence, different elements, then this is possible. Yeah. This is what we have discussed. So in the case of metric spaces, we have a countable base of neighborhoods of this X, limit point X. So we are able to construct the corresponding sequence which converges to X. Okay, I hope that everything is clear with this statement. So now we prove that item 3 implies item. Yes?
I'm sorry, maybe it's not too correct to because we use n to denote subsequence and no, sorry, I suppose you meant that, so sorry.
Yes, I guess. Yeah, the notation maybe not ideal, but I guess it's still understandable what is meant. But we have already discussed it many times that so this is a limit point. We have countably many neighborhoods to reach this point. And this is the thing which we really need in this setting. So this
Yes,
countable action makes the deal. Okay, so now we prove that item number 3 implies item number 4. So we use this lemma, which was before. So by lemma 211. Sorry. By lemma. This set K is totally bounded. Yeah, so once again, we assume that every sequence possesses a converging subsequence, but if the subsequence is converging, then it is a Cauchy subsequence, and hence this implies this property, which is if and only if, so which is equivalent to the statement that the set is totally bounded. So K is totally bounded. Moreover, K is complete. Since any Cauchy sequence, sorry, sometimes I switch into German, sorry, since any Cauchy sequence in K possesses a convergence subsequence by our assumption. Yeah, so due to our assumption, every sequence of elements, also every Cauchy sequence of elements from K possesses a converging subsequence, a convergent subsequence. But what does it mean? This means that this Cauchy sequence converges itself. Yeah, because if a Cauchy sequence has a convergent subsequence, so there is a limit of this subsequence, but but the points of Cauchy sequence, they become closer and closer to each other, and hence closer to this limit. Hence, the whole sequence converge to the same limit. So the Cauchy sequence, any Cauchy sequence converges, and hence this is exactly the definition of a complete metric space. So K as itself is a complete metric space. Okay, is it clear with the statement? Okay, perfect. Then we have to go further and open the next slide. So I give you a few seconds and we, so I see the time. We have still only 2 minutes, only 1 minute. So do you have more time or should we stop here and continue next time?
I have more time.
Is there anybody who has to leave immediately? Well, seemingly no. So let us then finish the proof of this theorem. And then after that, we stop. Okay, good. So now what is left? The left is that we have to show that item number 4 implies item number 1. And for this, we need an extra result. Oh, I was very economical. So this is a kind of exercise. So since every totally bounded set is separable, this we have already discussed in the remark 2.9. From this we can prove the following. So every open cover of A possesses an at most countable subcover. This is the so-called Lindelof property. Yeah, so compact set is the set such that any open cover of the set contains a finite subcover. But every totally bounded set is such that every open cover of A possesses at least at most countable subcover. So it's a weaker property than compactness. This is the so-called Lindelof property, but it is doable, so we need actually separability. So this is an exercise to show that this holds. And we prove the last implication, assuming that we already have this statement. So we prove now that item number 4 implies item number 1. So let u lambda in some big lambda, be an open cover of K. Then, so by Lindelof property, which is the exercise for you, there exists an at most countable subcover. So let me denote it as u lambda K, K in N, subcover of this set K. So assume there exists no finite subcover of K of the cover U lambda K. So now we consider this U lambda K as a new cover. It is an open cover, but at most countable. Well, if it is already finite, then that's it. But if it is just countable, then if we prove that there is a finite subcover, then we show that K is compact. So assume there exists no finite subcover of this new cover. Then for any n natural number, there exists a point xn in this compact set K, in this set K, which is totally bounded and complete. Such that xn does not belong to the union of first n sets U lambda K. Otherwise, if such xn does not exist, then this is already the finite subcover of K. So we have taken, so now since K is by our assumption totally bounded and complete, totally bounded and complete, then by lemma, which we have just proved, by lemma 211, there exists a subsequence x, how to denote it, x and m, a subsequence of this xn sequence, such that xn converges somewhere to some x, not xn but x and m. I see that I don't have place to write down further, but we have somehow preserved what is already written.
Maybe we can scale this text.
Maybe, but I don't know how to do it. So I can do it, and then, no, I can shift it, but I cannot make it smaller. But probably even this would be already nicer to have it like this. Okay. At least there is at least a few space. But you still follow me, yeah? Everything is clear what happens.
I think so.
Yes, okay. So what we do next? So since K is covered by this U lambda K, or by the whole cover of countably many U lambda K, there exists some element K0, natural number, such that this X, this limit point, yes? Yeah, so this limit point, of course, belongs to K because we assume that K is complete. Yes. So there exists K0 in N such that this X belongs to U lambda K0. Since X and M converges to X, there exists natural number big N such that X and M belongs to this U lambda K0 for any N bigger or equal this big N. And then this is already this contradiction. Contradiction with what? With the construction. With the construction. And construction was like X and M does not belong to the union U lambda K. Union K from 1 till M.
Excuse me.
Yes.
I think we are missing one part. And so in this point 4, I think we need that K is closed, right? It's not enough to only be
No,
bounded and
it
complete.
is complete. Complete. So each Cauchy sequence converges to the element of this set. Because we don't know if the ambient metric space if it is a complete space. So probably, you know, if our metric space X itself is just interval from 0 to 1 excluding 1, yes, then is it a compact set in itself? No. No.
Yeah, I see. So we have this convergence subsequence, and it's complete.
Yeah.
Then the
Yes. So this
okay,
X
then
belongs to our
X should belong to K.
It belongs to K because we have that we assume this. Yes. Sorry. I thought that I will do it in several pages, but yes, one has to see the whole structure of the proof, not like just a few parts.
I suppose it can be a little bit confusing for Vadim and me because in our courses we usually never had the notation that the set is complete. We usually say that the space is complete. And
yes, but when we speak about, yes, the metric space is just a set with a metric, yes? So any subset of a metric space is a metric space with induced metric.
Yes. It's we understand, but it can be a little bit confusing sometimes.
Yeah.
Sorry. Thank you.
Welcome. So I really try to, not to introduce the definitions which we don't really need. So there are a lot of different notions, and as I said, the more general setting there is, the more complicated situation and the more troubles may occur. That's why we consider, so to say, gold standard of Hausdorff spaces or sometimes metric spaces, where everything is almost as it was before. But nevertheless, with this almost, one should be always very careful. Okay, yes. So, yes, our course of lectures is supposed to be like a compact course. So we have skipped a lot of basic things which are assumed to be known from analysis 1, 2, I don't know. I hope that metric spaces are more or less discussed somewhere. Okay, so we have finished the proof, and the next time we will continue our discussion of compacts in different spaces, and we discussed some important criteria how to check that a set is compact in some important spaces. And I hope that already next time we will start the next chapter. I guess the next chapter would be about linear operator. It will be about Hilbert and normed and Euclidean normed and inner product spaces and many interesting stuff there. Okay, so see you next time. Well, I stop the recording. Wait a minute.
Professor, I'm wondering, could we have the answer to the homework next time? Last time?
So let me stop the recording and then we can speak further, yeah?
Okay, okay.